Hey guys, welcome to another video for pre-calculus. We are continuing our discussion on definite integrals. And in this problem, so in the previous video I discussed the concept of what a definite integral is and where do we apply it as far as finding the area underneath the curve. So in this video I want to work out an example of that. So here's our problem. It says use the limits to find the area of the region between the graph of y equals x squared and the x-axis on the interval of 0 to 4. So our interval is from 0 to 4. Let me highlight those in yellow. And then it wants us to find the area underneath the graph of y equals x squared. Okay, so here's our f of x equals, oops, not y squared, that's x squared. And from that all the way down to our x-axis. So we're looking for the area of that, what almost looks like a triangle there, okay, and I have lined in blue. So we're looking for that area, and we're going to use the definite integral to find that. So I have the definition over here, okay. So if you recall this definition from the previous video, remember that everything on the left is equal to everything on the right, and we're going to be using primarily, we're going to be using this notation to find our value, our area underneath that graph. So let's go ahead and get started, okay? So the first thing I want to do, because I want it ever present in my mind as to what I'm doing, I want to write my general equation, which is x squared, and then the interval from 0 to 4. Now this is important because as I start working on this formula here, right, as I start working on this formula, there's a couple of terms that I want to first find. I want to know what my x of I is, and recall that this, remember the formula for area is base times height, right, or length times width, and that's essentially what we have here. We have a length times a width, the width being delta x, right, that's my x final minus my x initial, if you recall, and then my length is my f of x, but it's not quite as straightforward as that in the sense that it's not length times width, because well, it is, but it isn't, because I'm looking for the area underneath the curve, not a straight line, which would be a lot more straightforward. So I want to find these terms. Let me erase what I have up here now. I want to find that x of I term, and then I also want to find, and I'm going to highlight it in green, that delta x. And as you recall from the previous video, these terms do have equations. So if you remember that your delta x, okay, that is your b minus your a divided by your n. All right, so that's going to be your that's going to be your high term, your 4 minus 0 divided by however many. Now remember that to find the area of a underneath the curve, we drew rectangles underneath that curve, right? And the more rectangles we had, the closer approximation we would end up with, and we want to use an nth amount, which eventually we'll end up using, highlighting in yellow here, we'll be using an infinite number of rectangles to get the most accurate area. Okay, so that's essentially that equation then. My delta x is 4 over n. Okay, so let me highlight these in yellow so I know that they go together. And so the next thing I want to do, now that I have that that delta x, that's going to help me find my x sub I. And again, if you recall from the previous video, the formula for x sub I is your lower term plus I times whatever your delta x is. Okay, let me just go ahead and write it out, delta x, right? And since I know what delta x is and I know what a is 0, right, my lower term, plus I times 4 over n. So I'm going to simplify this. This is essentially 4I over n, and that's what delta, not delta x, that is what my x sub I equals. Okay, and we'll highlight that in yellow too. Okay, so I have those two terms. I have this term here, right? And then I also have this term here. So I can start now simplifying my formula. Okay, so what is my general formula for this? So the integral from 4 to 0, or 0 to 4, of x squared d of x. And remember, anytime I have d of x, that means that I am now using an infinite number of terms, so I can find what exactly that area is. And I have my limit as n approaches infinity, because I'm going to use an infinite number of rectangles. And my upper term, ni, starting with 1, and then f of x, my length times my width. And I know what these are already, so let's go ahead and plug it in. So my limit as n approaches infinity, okay, sigma n I equals 1, and that's going to be, I know what my x of I is, right? X of I is right here, and that's going to be, because now remember that I have this is my formula, so then whatever my f of x is, whatever I have for x, which is going to be 4i, right? So I can replace this with this, but remember my general function is squared, so whatever I have there is going to be squared, which is 4i over n. Okay? So that can be kind of tricky, so take a minute maybe to think it over and make sure that we know what we just did before we move on. So this is my formula, f of x, right? So my f of x is x squared. So that means the real formula would be f of x sub I squared, because that's my formula. And now all I have to do is replace whatever I got for x of I, which is right here, 4i over n, and which is what I just did right here. Okay? Alright, so, and the next thing is I want to replace, what did I find for the value of delta x? But 4 over n, right? So all of this times 4 over n. Okay, well, I can now start working this out, and I can start simplifying this. Okay? So as I simplify this, I notice here that I have a coefficient term, or a term that I could use as a coefficient. So we can start simplifying this now. One of the things I want to do now, recall that in the last presentation, one of the last slides that I gave you, one of the last pieces of information was the summation formulas. Remember, there was about 8 that I gave you, and that's the goal. The goal to what I'm doing here, okay, is that I want to essentially isolate my I. Okay, that's what I want to do. I want to isolate that I. So I want to move everything I can off to the side as much as possible. And right now, the first thing that I see that I can take off to the side is my 4n, and I can kind of turn that into a coefficient. So it'll end up looking something like this. So I'm going to have 4n, right? I've moved it off to the side as a coefficient. So my new limit as n approaches infinity is 4n, and then my sigma I equals 1, and then I'm left with, and I'm going to go ahead and distribute my squared into all of my terms here. Okay, so I can just have it clean. I can clean it up a little bit. So that's going to be 4 squared. I already know is 16 I squared over n squared. Right. So notice that I have an I squared here. So that's going to give you a hint as to what you want on the right side at the end of all the work that you've done. And if you go to your summation formulas, you'll see that you're going to have an I squared by itself, and then you can see what it's going to turn into. So let's simplify that. Let's work that out. Whoops. Let's work it out to that point. So from here, what do I want to do? So remember that I want to get that I squared by itself. So I can actually put my focus on the 16 divided by n squared, and then factor that out also, right? So I'll have my new limit as n approaches infinity will be 4 times n, okay, and I equals 1, and I'm going to have 16 n squared, and then by itself I will have the I squared. You see how I did that? Okay, so now what I want to do, if you recall, I squared equals, or the, oops, what am I doing here? The sum of I squared equals n times n plus 1 times 2n plus 1 divided by 6. And that's the notation that I'm going to replace I squared with. So this term here, I'm going to hide it in green. This term here will be replaced by all of this here. That's what the summation formulas are good for. That's going to help me get closer to my final product. Okay? So then my new formula, and it's going to get messier before it gets cleaner, so we have to be okay with that. As n approaches infinity, okay, is 4n times 16n squared. Are you with me so far? Times what my I squared was, which is now n times n plus 1 times 2n plus 1, all divided by 6. Close parentheses. It may not seem like it, but I've actually cleaned it up. I've gotten rid of my I squared, and I am cleaning this up. Like I said, it does not look like it, but I am. So I have a denominator, and this is all multiplication, so I can multiply my whole denominator out, right? And I'll end up with a new limit, or the same limit, but just simplified. And it'll be, in my denominator, it'll be n times n, which is n cubed, times 6, which is 6n cubed. Okay? And then in my numerator, I can multiply all of this out. Now this is going to be a little bit messier, but not it's still very doable. So 4 times n is 64, and then I'm going to simplify this real quick, and that'll end up giving me 2n. Oh, actually, this is I feel like I'm missing something. Oh, my n. I can't forget my n. Whew, close call. So let's not forget about this n right here. This is n times 16 times 4. That's going to be 64n. And then now I'm going to multiply this times that. Okay? And that'll be, let's see what's that going to be. It's going to be 2n squared plus 3n plus 1. Okay? And there we go. So I can simplify this still. I can simplify this. I have my n's. Let's see here. What can I do? I can factor this out, my coefficients there. So I'll have a limit of, as n approaches infinity, I'll have 64 divided by 6 times, okay, so then, excuse me, I need to go back up here. I need to distribute this n to these three terms. That's going to give me 2n cubed plus 3n squared plus n, and then all of this divided by my n cubed. Yes? So then my limit, my simplified limit as n approaches infinity is 64 divided by 6, and now I can separate these two. I'm going to have 2n cubed over n cubed plus 3n squared over n cubed plus n divided by n cubed, close parentheses. And so we're still simplifying. This is a long problem, isn't it? 64 divided by 6, which I've recognized a long time ago that I can reduce that, but I'll do that later. So working at the top, this reduces, my n squared reduces, that we get rid of that, we get rid of that, and that becomes squared. So now let's see what my new problem is. I essentially have 2 plus 3 over n plus 1 over n squared. Now this is pretty simplified. At this point, now I can start plugging in my infinity, okay, because I won't get an indeterminate, if you recall that from the previous section. So I can put my infinity now with my n's, right? So I'll have the limit as n approaches infinity, 64 divided by 6. Yes, it'll be 2 times 3 over infinity is 0. 1 over infinity squared is 0. So I am left with, as n approaches infinity, and then I know that my 2 can cancel out and now have 3. So then my final answer will be 64 over 3. So my limit as n approaches infinity will be 64 over 3, or 21 and 1/3. What does that number mean? Okay, what does that number mean? All that means is that the area underneath this curve, if you remember from the beginning, the area underneath this curve, okay, this curve right here is, after all that work, is 21 1/3 square units. And that's that problem. Okay, guys, I really hope this helped. I'll work out another one and in efforts to try to simplify this concept. Okay, just keep the big picture in mind. I'm looking for the area of the underneath the curve within a given interval, and in order to do that, I need to use definite integral definition. Okay, and everything we just did was in simplifying that, so I can finally come up with a nice clean number like 21 1/3. Okay, guys, thanks for watching and good luck in your study.